In this video, we're going to balance half reactions. So we've already talked about half reactions, GIR and LEO. Gain of electrons is a reduction, so that's where the electrons are in the reactants. But LEO, losing electrons, is oxidation. We use the add electrons to the side of the half reaction that is more positive to balance out the charge. Electrons being negative, that makes it possible. Now, balancing a half reaction in an acidic solution is not real tough, but it's certainly harder than just adding electrons to the reactants or the product. Though we will do that as well. Key to note is in an acidic solution, there's lots of water and lots of hydrogen ions. And what that allows us to do is balance oxygens using water and then finally balance hydrogens using hydrogen ions. At the end, we put our electrons in to make the charge equal. So here's an example. I have manganese 2 becoming permanganate ions. So the manganese 2 and the manganese are already balanced, right? One manganese atom in both. And the starting point for us is to make sure that we've got everything but the oxygens and hydrogens balanced. We do. But my oxygens aren't, right? The products has 4 oxygens and the reactants have 0. So this is where I use my waters to balance out these oxygens. So if I add 4 waters to my reactants, now my manganeses are balanced and I have 4 oxygens in both places. But we now have 8 hydrogens in the reactants and none in the products. Well, there happen to be a lot of hydrogen ions floating around, so I can put 8 hydrogen ions in the products, and now my manganeses are balanced, oxygens are balanced, and my hydrogens are balanced. But over on this side, I have 2 positive charge, and over here I've got 1 negative, and I have 8 positives. So this side has 7 positives, and this side has 2 positives. I can make that equal if I put 5 electrons on this side, because if I have 5 negatives, that leaves me with a total of 2 positive and a 2 positive. So now I've got both all of my atoms as well as my charge balanced, and my electrons are a product. So this is losing electrons and is oxidized. My manganese 2 is being oxidized to become permanganate. This is in an acidic solution. On page 565 in your textbook, they give you a question. So this is an example question from page 565. And it says nitrous acid, which is HNO2 AQ, it's a weak acid, so it doesn't break into its ions, becomes nitrogen monoxide gas. So I start off by balancing everything but hydrogens and oxygens. So 1 nitrogen, we're good. This has 2 oxygens, but this only has 1. So I have to add a water to give me 1 more oxygen, right? So now I've got 1 and 1 nitrogen, I have 2 and 2 oxygens, I have 1 hydrogen and I have 2 hydrogens. So if I add a hydrogen ion here in acidic solution, now these are all atoms are balanced, but my charge isn't. I have a 1 positive and a 0. So I add an electron to this side because it's more positive to balance the charge. 1 positive and 1 negative is 0, and this has 0. So since electrons are a reactant, this is the gain of electrons reduction, and that was what we were supposed to prove anyhow, right? So this is the balanced half reaction for nitrous acid being reduced to form nitrogen monoxide gas. So that's in an acidic solution. But in a basic solution, we have a lot of water and we have hydroxide ions. But we don't actually have many, if any. Well, we'll have 1, but we don't have much in the way of hydrogen ions. That being said, our strategy for this is to balance like it's in an acidic solution. So I'm going to take my copper metal, and it's going to become copper 1 oxide. Keep in mind copper 1 is this, and oxide is a 2 negative. So it's going to be Cu2O, solid. And I need to balance my coppers, so I've done that. I have 1 oxygen here. Well, I'm going to balance it in water. So now I've got 1 oxygen on both sides. I'm going to balance it like it's in an acidic solution. I'm going to put 2 hydrogen ions here, even though they're not around. and I'm going to add my electrons. So this has 0 charge, this has a 2 positive, this is a more positive side, so I took the electrons. That's the balance if it was an acidic solution. But since it's basic, these are not present in any large quantity. So it won't be this. But there are lots of hydroxides. So what I can do is I can replace this with a hydroxide. So if I add 2 hydroxides to the products, I need to add 2 hydroxides to the reactants, right? If I do the same thing to the reactants and the products, it will remain balanced. But what happens is this becomes 2 waters, because a hydrogen ion and a hydroxide will become water. So my reaction is 2 copper solid plus water plus 2 hydroxides makes copper 1 oxide plus 2 waters plus 2 electrons. Well, it doesn't make sense to have water in the reactants and the products, so I'm going to get rid of this one, and this will become a 1. So I have 2 copper solid plus 2 hydroxide ions become copper 1 oxide solid plus water plus 2 electrons. And if I go back and I double check, I should have still got a balanced charge, 2 negative, 2 negative. I have 2 coppers, 2 coppers. I have 2 oxygens, I have 2 oxygens, I have 2 hydrogens and 2 hydrogens. So this is balanced. And since the electrons are a product, this is losing electrons, it is oxidized. Copper is being oxidized to become copper 1 oxide. And that's the balanced reaction. So we're going to always balance the atoms. We're going to balance the oxygens with water, balance the hydrogens with hydrogen ions. If it's in a basic solution, then I cancel out the hydrogen ions by adding the same number of hydroxides to the reactant or product. Make some waters, cancel out any redundant or repetitive waters, and get my net reaction. So it's really not a lot harder, but it's an extra step. Where this will be useful is later on we're going to use this same strategy for not just half reactions, but whole balanced chemical reactions, whole balanced redox reactions in acidic or basic solutions.